So good morning, everyone. My name is Michael Busch. I live in San Francisco, where Twitter's headquarters is located. I lived there for about 8 years now. I'm actually German, so you may recognize that when you hear my accent. But yeah, I lived there for 8 years. Actually, I'm wondering, am I supposed to get a remote control for the slides, or cool? Yeah, these are exciting times right now for Twitter. And I want to walk you in. The agenda is, in the beginning, I want to talk a little bit about some of our numbers we're dealing with at Twitter, and I also want to mention I've been there for 4 years, and I want to explain a little bit how search evolved in the last 4 years. After that, I want to give you an overview of our search architecture, how we use Lucene, what the different components are, like on a higher level. And then in the second part of the talk, I want to go really into some technical details, what modifications we made to Lucene to support support the big scale numbers that I'm going to talk about, and especially how we support real-time search. So in the last part of the talk, I want to explain how our posting implementation differs from Lucene's and why we had to make those changes, and also what other changes we made recently, which are going to be very, very interesting when we talk about contributing all this stuff back into the Lucene code base. All right. Quick question. How many of you guys have seen my talk like 2 years ago in Barcelona? Okay, not too many. That's good, because in the inverted index chapter, I want to repeat a little bit what I talked about back then, just to get everyone on the same page about what an inverted index is. I usually like to include a few minutes of that into my talk, so that everyone kind of gets reminded of how Lucene works under the covers. Yeah, so now Twitter has has more than 230 million monthly active users, and 500 million tweets are sent every single day, basically. That's, of course, a huge amount, even though tweets are short, but that's still a huge amount of data. And that basically means that we have already seen more than 300 billion tweets since the company was founded in 2006. So it's not quite 15,000 years old yet, but people haven't been tweeting for 15,000 years, but we still have a huge amount of tweets. And we had a world record, which was 33,000 tweets per second, I think this year. And I remember when I joined Twitter in 2010, we were really nervous about this number going above like 800 or 1,000. We were nervous that the search engine would go down actually if it exceeded 1,000 TPS. And now we can easily handle peaks like this one. Also, we have more than 2 billion search queries every day. That includes API queries and user-entered queries, which of course is also a huge number, which is like, I don't know, 30, 40,000 queries per second. All right, so in 2008, Twitter didn't really have any search yet. Twitter was pretty small still. And Twitter acquired a small company called Surmise. It was a small startup, only a few people worked there. And they worked on different technologies. One was actually real-time search implementation specifically for tweets. And that was actually interestingly based on MySQL, which is not really text search engine, but it worked pretty well. But soon, when Twitter started growing and those numbers that I talked about increased, this engine wasn't really working very well anymore, the MySQL implementation. In early 2010, I joined the company, and we knew we needed to re-implement kind of the inverted the indexes, and wanted to switch to like a more modern technology like inverted indexes. Since I was a Lucene committer, we started looking into Lucene and made a prototype based on Lucene that had some changes specifically made for real-time search, which we need at Twitter. And that shipped in end of 2010, beginning of 2011. And replaced MySQL, and we really saw like orders of magnitude better performance. And this system is still in use now and has grown with the company, and is still performing really well. Of course, we have made further improvements since then. For example, in 2011, we launched new product features, like you can now search for images and videos. If you search on Twitter, you get not only tweets in your search timeline, but you get like Vine videos and popular images and that kind of stuff, which of course is coming from search index. Oh, by the way, I haven't mentioned Earlybird yet. Earlybird is our internal code name for our Lucene implementation. So everything in Twitter always has bird names, every project. So this one is called Earlybird. Yeah. We also implemented index compression, which is very actually similar to what Lucene is using nowadays. And we also implemented relevant search. Back then in 2010 and 9, you could only search for all tweets ranked by time. Now we also, because there are so many tweets now, we also offer relevant search. So when you just enter a query, we show you the best tweets. Still ordered by time, but we kind of filter out the not so important tweets. But you still have the option actually to search for all tweets if you want to. Then in 2012, 13, beginning of 13, we launched what we call archive search. Before that, you could only search the last X days of tweets, like a few days, which people were pretty unhappy with, of course, because there's 300 billion tweets which have a lot of information about past events, like Hudson River landing, when the plane landed on the Hudson River. That was a big event on Twitter because it was first actually announced to the world via a tweet from a person who was on the boat there in the Hudson, on the Hudson. So yeah, we launched archive search, which actually uses vanilla Lucene, completely unmodified Lucene indexes, which is exciting. And then very recently, actually, we switched our real-time index, our Earlybird indexes, to a new posting list format that supports still all the real-time optimizations, but not only optimized for tweets anymore, but you can now use it for kind of all types of documents like Lucene, which is something I'm going to talk about later, and which is exciting because now that gets us a big step closer to actually getting this technology into Lucene so that everybody can benefit from it. Okay, so here's a high-level picture of our search architecture. Let's concentrate on the upper part for now. So we get, of course, a real-time stream of tweets. As I said earlier, like 30, how many was it? Like 500 billion tweets per day. 500 million tweets per day. So we get a stream of raw tweets. And they get fed into our analyzer/partitioner, which is a component that takes those tweets and does stuff like normalization, tokenization, which is called in Lucene analyzing the documents. It does geocoding. If you have shortened URLs, it expands the URLs, and does a lot of stuff like this. And prepares the tweet for indexing. It stores all that pre-tokenized content in Thrift objects. I don't know if you guys are familiar with Thrift. It's a data serialization format that we're using in Twitter. And what it also does, it does hash partitioning. So of course we don't have all tweets in like a single index. So I'm going to show the cluster layout in a second. But this component actually takes the tweet ID, mods it by the number of hash partitions that we have, and then arranges the data in different hash partitions. I think my remote stopped working here. Okay. So that's what the analyzer is doing here in partitioner. So you can see raw tweets come in, analyzed tweets come out, and get sent to the Earlybird indexer. That Earlybird index, as I said, is a modified Lucene version optimized for real-time search, which I'm going to talk about. One of the big differences compared to Lucene is that if you have used Lucene's near real-time search feature, we don't have to actually flush any in-memory data structures to disk in order to search them. In Lucene, every time you actually want to be able to search the most recent documents you added to an index writer, you have to call reopen on the index writer or update, and it will actually internally flush its buffers to disk or to RAM directory, and then you can search it. That's kind of inefficient for us because in Twitter we want to be able to always search the most recent tweets. So we would have to reopen the index writer all the time, which would lead to a decrease in indexing throughput if you had to flush all the time. So one of the big changes we made is that you actually can search the buffer in the index writer while you are appending to it. It's all in memory. These indexes are all in memory, and they're hash partitioned using a static layout, which is explained on this slide. So every Earlybird index contains a certain number of documents. In the real-time case, in real-time index case, it's I think 8 million to 16 million tweets. And every Earlybird index is replicated a certain number of times for redundancy and also for just to scale our queries per second. Then, as I mentioned, we have a fixed number of hash partitions. And it's very simple technique. We just mod the tweet ID to figure out in which hash partition a tweet should go into, and then index that in the corresponding indexes. I think the slide doesn't actually fit fully on the screen. Yeah, there's probably nothing important on there. The indexes are sorted in time order. So what's on the upper end of the slide are the most recent tweets, the most recent Lucene segments. Going down are older segments. So this means that the segments on the top here are the ones that are not complete that we are writing currently to. So these ones we can always append to. And the older segments, when they are full, when they reach 60 million documents, then they are fixed and they can't be updated anymore. And you can think of the real-time index in Twitter as a cache. So it means that it's kind of rolling, sliding window of the most recent tweets. Because basically, if we have finished a new time slice here, or time slice is the same word for segment, basically. If we have finished a new time slice, then we discard the one on the bottom. So we always have the same number of tweets in our in-memory index. Yeah, so since that is kind of a cache, and I said earlier we were only able to search the most recent tweets, we recently launched the tweet archive, which is a whole different ingestion pipeline here in this picture, which is on the lower half of the slide. So basically, all tweets in Twitter are stored in HDFS. And to build these archive indexes, we actually use MapReduce jobs. So we read the raw tweets from HDFS, and daily jobs actually create from these raw tweets again the analyzed content. So they analyze the text similarly to the real-time analyzer that I talked about already. Aggregates metadata like how often was the tweet retweeted, unfavored, and that, like we have of course a lot of metadata. It aggregates all that, tokenizes text, normalizes text, and then stores that again in our thrift format. And then we build archive indexes from that. And these archive indexes currently are on Lucene 4.4 standard, no changes basically to the index format. They are reverse time sorted, and that's actually an advantage of building them in MapReduce or building them offline, that we can change the sort order of the indexes. So since we still actually, even if we do relevant search on Twitter, we still show the search results in chronological order, like from new to old. So that's why it still makes sense, even though we do relevance filtering, it still makes sense to actually sort them new to old for early termination reasons. Otherwise, the cluster layout is very similar to the real-time search layout. It's maybe a different number of replicas and hash partitions, but it's a very similar, simple hash partition layout. The interesting part about the archive index is that we actually currently have two tiers. One tier is a smaller one, the upper one here, which is an all-in-memory index, Lucene index, vanilla Lucene index, that contains a small number of the best tweets of all time, and best, of course, is something I cannot tell you how we measure that, but of course it includes stuff like how often was the tweet favorited and this kind of stuff. So of course we use engagement signals and like a lot of other signals to figure that out. We have a second tier index that's on SSD, again a vanilla Lucene index, which is much bigger, of course. It supports less max QPS, which is fine, because what we first always do is we hit our in-memory archive index, and only if we didn't find enough search results, then we actually go to the SSD index, which still has actually really good latency. SSDs are fast nowadays, but the throughput is not as good, of course, as in memory. So the IOPS of an SSD is still like 1 or 2, or probably 2 orders of magnitude lower than compared to memory. So we are limited basically by IOPS here. But yeah, it's good because it's okay because we use the in-memory archive index to search first for your best tweets. Then we have a component that we call the Blender. The Blender is a thrift aggregation service, which basically takes a search request, like you enter a query on your iPhone or website, goes through some stages in the Twitter stack, and at some point the Blender receives the request as a thrift object. And the Blender is a workflow management system. It knows a lot of different services within Twitter. It knows our different search indexes, like the real-time Earlybird index and the archive index. It also knows like other things like how to map usernames to user IDs and like a lot of different internal services. And it can call all these services, and it knows exactly for each query which services do I need to call to satisfy the query. So for some queries, we need to call more services than other ones. For example, if you search for something like, best photos near San Francisco, right? So now we have to figure out what does near San Francisco mean. We have to talk to a geo service. The Blender also figures out what services can it call in parallel, which ones can it only call serially. So for example, in parallel, it could probably call those two indexes and get results from both, but it could not, in my examples that I just mentioned, call the geo service at the same time as Lucene, because it needs to know the location before it can call Lucene. But yeah, the Blender takes that request, fans it out to multiple components. For example, our two indexes here, receives the results, merges them together, does maybe some post-processing, some ranking, some dupe filtering, and sends it back to the caller, and then we can render it on your device. That's pretty much it. One thing I haven't mentioned yet is I said most of these segments, after they are full, they are complete and not mutable anymore. It's not completely true. We have another stream of updates, which can be deletes. Everybody can delete tweets, or if there's new engagement on a tweet, like if you favorite it, we send these signals to these different indexes and update in-memory data structures. One difference that Earlybird has compared to Lucene also is that we can update column stride fields, or I think they're called doc values in Lucene. Something Lucene is catching up with now. It's much easier for us because for us it's all memory. We can overwrite a lot of these signals just in place. In Lucene it's a little different. You have to talk there about merging. But yeah, Lucene is getting this feature soon too. But we use these updatable column stride fields to update all these signals, and they come in through a different pipeline. Okay, any questions so far about the search architecture? Sorry, the question was the hash based on tweet identifiers. How do we assign identifiers to tweets? That happens already like way before the tweets even get to the search engine. We have a project, I think it may even be open source, called Snowflake, and it's a distributed ID generator that can generate unique IDs for the different tweets. And I think there's blog posts out there how exactly it works. But yeah, every tweet gets a unique ID assigned, and then the tweet carries that ID already when we get it in search, and then we just use that ID and mod it by the number of hash partitions. Okay, how many people know how an inverted index works? All right, I'll be quick with that. So yeah, Lucene and Earlybird and all these search engines use an inverted index to do fast retrieval. And if you look at these 6 documents and you want to find a word in these, it would be not very smart to just keep searching until you find the word. It would be very slow. That's why we built an inverted index. What it basically does is it takes all documents, finds all unique terms in all these documents, and builds a dictionary that's shown here on the right side. So these are all alphabetically sorted terms that occur in these 6 documents, or unique terms. And then on the right side, we have something called the posting list. So for example, if you want to search for the word keeper, which occurs in documents 1, 4, and 5, you could quickly find it here in the dictionary. It's like basically in a book. If you read a book, and in the end, you have also like a dictionary, a lookup table, right? There's pages. It's very similar here. You find the word keeper in the dictionary. It's sorted, or it could be a hash table in Earlybird's case. Find it quickly. Look at the posting list, and it tells you the document occurs in. The term occurs in documents 1, 4, and 5. So now, when we talk about data encoding in an index, the majority of all the data is really in the posting list. The posting lists occupy a large percentage of your entire index. So they have to be stored very efficiently, and ideally it would be nice to compress them really well. So if you look at the doc IDs up here, if you, for example, had a posting list with numbers 5, 15, 9,000, 9,002, 100,000, and so forth, then those numbers are pretty big. What Lucene does and Earlybird does is we do delta, sorry, not actually, Earlybird doesn't do it. What Lucene does is we do delta encoding. So we don't store there the number itself, but the difference between the current posting and the previous posting. So for example, instead of 15, we could store 10. 50 minus 5 is 10. And instead of 9,002, we could actually store the number 2, because that's the difference between 9,000 and 9,002. So why does it help us? It helps us if we can actually store smaller numbers in a more compressed way. So Lucene used to use, it's actually slightly different now, or yeah, it's using a different compression strategy since version 4.3, I believe. But before, Lucene has always used VN compression. And how that works is you don't always use 4 bytes for each integer, but you use a variable number of bytes. And you actually use only 7 bits of a byte to encode the value itself, and use the first bit to indicate if the next byte following the byte you're currently decoding is part of the same number. So for example, if you want to store number 5, we mark the first bit, the first bit is marked 0, so now the decoder knows, okay, I only need to read this 1 byte, and then I know what the value is. I don't have to read the next byte. However, if you store a bigger number like 8,000, that doesn't fit into 7 bits, obviously. 7 bits can only store a number up to 127. So in this case, we need 2 bytes, and the first bit of the first byte would be a 1. So now the decoder actually knows, oh, I have to also decode the next byte to figure out what my overall value is. And then the next byte, then it reads the next byte. That starts with a 0, and now the decoder knows, okay, I have read all bytes for this particular value. So now we only need a variable number of bytes for numbers, and now it makes sense to actually make the number smaller to save space. That's why we do use delta encoding. So some problems here, and that's why we had to change this encoding in Earlybird, is that you can only read these posting in old to new direction, in the direction you have written them in. Because delta encoding, every posting depends on the previous one. Oops, am I doing this? Every posting depends on the previous one, because we have this delta encoding. So it's only possible to read these posting lists in old to new direction. And now if you think about Twitter, we always want to return the most recent tweets first, because those are the most interesting ones in real-time search, right? So we would actually ideally like to read the postings in the opposite direction, because then we could early terminate after we found enough results and don't have to read the entire posting list. So that's why we wanted to change this, to be able to read in the opposite direction. The other problem with using VNs is that in Java, or probably in any programming language, you cannot write a variable number of bytes atomically. So you can write a 32-bit number like an integer. You can write that atomically. Atomically means that one thread can write it, and a different thread will never see a value other than the old or the new value. It will not get any dirty reads. It's a really atomic operation on a low level, on the CPU level. If you want to store a number with multiple bytes, like with 3 bytes, it's not impossible to store that in Java atomically. And for our concurrency model in Earlybird, it's very important for us that we can actually write these numbers atomically. So that's why it also doesn't work for us in Earlybird to use variable number of bytes per posting. Which brings me to the implementation of Earlybird's posting lists. The encoding actually, this is what we used to use. Very recently we changed this slightly, and I'm going to cover what it looks like now. But it used to be extremely simple, actually. Every posting used to be one integer. And we split up that integer into 2 parts. The first 24 bits are the doc ID itself. That means it can have at maximum a value of 16.7 million. That's also where the maximum segment size that I mentioned earlier comes from, where I said every segment can only have 16.7 million documents. that's because of this limitation that we only use 24 bits for the doc ID. That leaves us 8 bits, and in these 8 bits we store the position of a term within a document. We need to store the position because if you do, so for example, phrase queries, if you search for San Francisco in quotes, we need to know that San and Francisco are next to each other. For that reason, we have to store not only the doc ID, we also have to store in Lucene the position of a term. So now tweets are very short, 140 characters. So even if you have a Japanese tweet that doesn't use white spaces and you would tokenize it into 140 tokens, you would still not get more tokens than 255. Which is why we said, okay, 8 bits are enough for the position, and we're going to reserve a fixed number of bits for that reason. So now the cool thing is actually, you can now, because it's so simple, because we don't do delta compression or anything else, you can read this in both directions, right? No posting depends on the previous one, so it's very easy to just decode them in reverse order. So we write them here in left to right direction, and we read them in right to left direction. And for example, if you want to return 3 search results, you can start searching, and after you found 3 results, you can actually stop. You can early terminate, and you don't have to look at the rest of the posting list anymore. If you can only read in left to right direction, it's a much harder problem. You cannot do it as efficiently to find the last 3 results, especially if you don't know where the posting list ends, because index writer is appending to it. So this is a very simple but very efficient implementation. Now, how does it work to store all these postings? I'm going to cover this also pretty quickly now, and after that I will more focus on how we are changing this encoding to support documents that have more than 140 characters. So if you remember earlier when I showed you how an inverted index works, that we have a dictionary component and then we have also posting list. So I'm not going to cover now how we encode a dictionary. There's multiple different implementations. Lucene's is actually completely different from ours. Ours is an in-memory hash table, very, very simple. Lucene has some fancy FSTs and that kind of stuff. So I don't want to focus on the dictionary, but I want to focus on how we actually store posting lists. And the objectives for this storage of posting lists is that we want to store a lot of basically a posting list is a linked list, right? So we want to store a lot of these posting lists in a very efficient way. And the challenge here is if you see a tweet with a term you haven't seen before, maybe a new hashtag, for example, at that point you have no idea, are you going to see this term again? Because maybe it's like this new theme or a meme or a new breaking news. So maybe now you're going to see this 5 million times, that hashtag, and you need to allocate a lot of memory for that corresponding list. Or is it a unique term, like someone made up some funny word, and you're never going to see it again? In this case, of course, you don't want to allocate a lot of memory. So the first time you see it, you have no idea what to do. Also, since it's all memory, we have to be very careful about garbage collection. It should ideally use a constant number of objects, this whole storage, and should be independent on the number of objects that we use should be independent on the number of postings. And yeah, it should be possible to read them in the opposite order, as I said earlier, and we need to be able to, so the log-free part is something I talked about 2 years ago in Barcelona. I can't talk about it right now, but the talk is online, so I encourage you to check that out. It's actually my favorite topic about Earlybird, but there's not enough time today to also talk about this one. But what I said earlier, it's important for this threading model that we can write the postings atomically. And if you check out the other talk, you will understand why. Okay. So how does this work? For now, imagine we have in memory 4 levels of integer arrays. And these integer arrays on each level can grow into this direction by allocating new integer array blocks in Java. But you can kind of, for simplicity, just think of we have 4 arrays that can individually grow, and we can kind of forget that they are backed by multiple blocks. So you can just think of 4 different arrays on 4 levels. On each level, we can allocate what we call slices, which can be assigned to particular terms. So on the lowest level, we can allocate a slice with a size of 2. On the next level, we can allocate a slice with a size of 16, and so forth. 128, 2048. On each level, we can allocate a multiple of these slices, but they will always have the same size, right, as shown here. So now when we see new terms, the hashtags that I mentioned earlier, we don't know yet, as I said, we don't know how often we're going to see it. So the first thing we do is we go to the lowest pool and allocate a new slice, 2 integers for it. So now we have room for 2 postings. We have seen the term, of course, already the first time, so we store that in that slice, and we will have room for another occurrence of this term. So let's say we see the term 3 times. We have stored the first 2 occurrences in the slice here. Now we see it the 3rd time. Now we say, OK, it's probably likely if we see it the 3rd time, we're going to see it more than like a bunch more times now. So now we go up a level and say, OK, now we allocate 16 integers additionally. And we can store the next 16 occurrences of that term in that slice. So then if you have seen it 18 times, we go up a level. If you have seen it 128 plus 18, whatever that is, then we allocate a slice on the highest level. Then we have room for 2,048 more occurrences. And if you see it even more often than 2,200 or so, then we stay on the upper level and just allocate slices on the upper level, right? Yeah, so now the question is, how do we search this? As I said, we want to search in the opposite order of the insertion order, right? So we kind of write in this order, but we want to search in this order, in this direction. So there's a missing piece here, which is how does it know if it searches the slice to get to the previous slice, right? So we need to be able to link the slices together to make it really a linked list, a reverse linked list, basically. Again, this was a posting encoding. Just as a reminder, it fits into 1 integer. The cool thing is that actually any pointer to any of these postings also fits into 1 integer, because they are encoded like this. We take a 32-bit integer and divide it into 3 sections this time. The first section uses 2 bits to indicate which pool we are using, which level basically. Remember, we had 4 levels. So these 2 bits are enough to determine on which level we are talking about. The next section is the index within the level, which slice we are talking about. So for example, this would be level 0. This is the first slice, second slice, third slice. So the slice index indicates which slice we are talking about. And then depending on which level we are, we need a certain number of bits for an offset within a slice, right? On the lowest level, you only need 1 bit. Because the slice size is 2, we only need to say it's the first or the second integer. If we go up, we may need up to 11 bits to indicate which particular posting we are talking about. So that's how we can encode a pointer also into a integer. And the cool thing is now that we can store the pointers itself in integers, we can store them in the same arrays. And basically, we can say, OK, the first integer in a slice is not a posting, it's actually pointer backwards to the previous slice. And now the whole thing looks like this. When you enter hashtag in the search engine, we first look it up in the dictionary, we find a pointer to the most recent posting, and then we search backwards in this slice. Maybe we early terminate because we found enough results, but maybe we can't early terminate. So then we reach the beginning of the slice, say, aha, it's a pointer to the previous one, we follow it, and then we can decode the next slice and so forth until we either early terminate or we search until the very end, or beginning, I guess. Does that make sense? Cool. I'm sorry? So the question is, why do we use these 2 bits? Because we should know which level we are referring to. We don't, right? Because here we don't know if we are going to stay on the same level or if we are going down a level.
Yes, but there are only these 2 possibilities.
Okay, there's 2 possibilities. True, we could save a bit. However, this pointer that points from the dictionary to the most recent posting uses the same encoding. And of course, if we have seen the term only 1 time, it could certainly point to this level. So it couldn't really point to anywhere. So that's kind of the answer. I mean, also, we don't really need the bit for anything else. Which is something I usually don't say, but yeah. So as a summary for this posting encoding, ints can be written atomically in Java. Again, important for our threading model. We can we can read these posting lists in backwards order. Every posting is a possible entry point. Basically, that means you can, throw a point. You can follow a pointer to anywhere in this list and start searching. There's no context you need to know. We can do efficient skipping because it's fixed sizes per posting. So you can say I want to skip over 10 postings without needing additional data structures, even though there are better approaches which I'm going to show you. One thing I have not mentioned yet is that a disadvantage of this encoding is, especially when we talk about bigger documents, that let's say you have a document that contains the same term multiple times. In tweets, that's not very likely because tweets are so short, but it could still happen if it's like a stop word like the or a. It could also in tweets occur multiple times. What we do, that's different to Lucene, is we just store the entire posting multiple times. So we repeat the doc ID. We write the same doc ID twice in that case. That's fine for tweets because, again, that doesn't happen very often. But if you talk about large documents, if you index like multiple page documents, of course that will have stop words many times, and you don't want to encode the doc ID like 1,000 times if the is 1,000 times contained in your document. Lucene does it differently. It actually stores the doc ID and followed by a value called the term frequency. That was actually earlier on the slide about the inverted index, which is the length of the posting list. So Lucene stores the doc ID once, then the term frequency, and then it stores the positions. So clearly a disadvantage if we want to use this encoding for larger documents. So that brings us to the new posting list encoding that we recently switched to. So the objectives are, we want to support 32-bit positions, not only 8 bits, to be compatible to Lucene's posting list API. We want to support payloads, which, do you guys know what payloads are? Probably most of you do. With every posting, you can store metadata in a byte array that can have any number of bytes you want. We want to store term frequency, which I just mentioned, instead of repeating doc IDs, because it just doesn't make sense for large documents to repeat the doc IDs. We want to keep our concurrency model, very important, otherwise the whole approach doesn't really work anymore for us. We want to stay space efficient for the tweet use case, but we want to add the flexibility for large documents. But we want to keep the space optimizations, and we want to keep the performance that we are seeing right now. Okay, so now when we look at the Lucene posting, it basically consists now of this. It consists of a doc ID, then of the term frequency that I mentioned, and then of one or more of these position payload pairs for this particular document. In the new posting list encoding, what we want to do is we want to keep the fact that these postings that contain the doc IDs are fixed size, are integers, because again, they can be written atomically and for a number of other reasons. And then we can also continue using that memory storage model that I showed you. But we want to support variable length for these positions and payloads. So what Lucene does and what we are going to do what we are doing in Earlybird now too, is actually we want to store them in separate data structures and separate streams. And the upper one is basically what I have talked the last 10 minutes about. That is, every of these yellow boxes is basically one integer, and it contains the doc ID as before, but now it may actually contain the term frequency instead of the position for the 8 bits. And all the positions and payloads can be stored in a separate data structure where for each posting we can have variable length bytes here. The problem now is, how do we correlate the doc ID posting with the corresponding position payload pair posting? It's not an easy problem because you do not want to store a pointer for every single posting, because then the pointer itself would be as big as the posting itself, right? We would also use probably a 32-bit integer. Since these are 32-bit integers, we would actually double the amount of space we need. But because of our concurrency model, it's also there's a lot of limitations we have because we write everything in a log-free way. We have to make sure we don't get dirty reads and that kind of stuff. So it's kind of a difficult problem how to encode these pointers. Right. So now the idea is to actually use an embedded skip list. And skip list is something Lucene uses for speed. We introduce them here now for two reasons, for speed, but also for these pointers. And the idea is that at regular intervals in this doc_id stream, we inject these skip points. And a skip point contains a pointer to where in this stream, in the position payload stream, the corresponding section starts. And now the cool thing is that we actually don't need to that we don't need too much space to encode all the pointers, but we have them regularly enough so that it works that it's performant enough. And if you look at how these are stored, if you take a slice, for example, on the lowest level, remember there was a slice on the highest level, 2048 integer slice. We changed the encoding now so that basically it has a header, and the header contains all the skip entries that I showed. Logically, the skip entries are kind of evenly spaced over the entire posting list, or the slice in this case, but now we store them together in the header of the slice for cache efficiency reasons and simplicity reasons. So the first integer again has, as before, has a back pointer, and the next section in this header has now the skip list for all postings in the slice that contains the pointers to the position payload stream, and it also contains the doc IDs at the positions where these skip points are. That's helpful if you, for example, want to skip to a certain doc ID. You don't really have to scan this whole stream. You can actually just scan the skip list, like Lucene does that stuff too. You can just scan the much smaller skip list, find the right entry point that's close to where you want to go, skip there, and then search for the actual posting between those two skip points. And then when you actually find that skip point, you also read the corresponding pointer into the position payload list and know where the corresponding bytes start in that other storage. We also store slice ID, which I don't want to talk about right now because it's a little subtle what we use it for. But I can just tell you that it's also it's actually specifically made for compatibility with Lucene. Lucene has point-in-time semantics, which means when you open an index reader, Lucene sees a static snapshot of your index. With our encoding, it's very hard. It used to be very hard to actually return a length of just the length of the posting list in a point-in-time semantic. That because we are appending to the posting list all the time, so the length is always changing. But an existing index reader wants to see what was the length of the posting list at the time when I was opened. So using slice IDs, we can actually, if an index reader knows it's pointing at a particular slice, it can easily from the slice ID calculate what is the length of the posting list up to that point. And actually an O of 1, like Lucene, return the length of the posting list, which is going to be very important when we want to contribute this back to Lucene. Yeah. So this was the old encoding of a posting itself. So now, as I mentioned, we don't want to use these 8 bits only for the position anymore, but now we want to actually store also the term frequency in there. So we change, but we also want to keep the optimizations we made for tweets. So one observation is that yes, tweets can have 140 characters, or they could have 140 tokens if we have a non-white space language, but most of the times they don't. I mean, normally, I don't know, tweets maybe have 10 words on average, I don't know how many, but roughly like that, I would guess. So the number 10 you can store in 4 bits. So you almost never need the full 8 bits to store the positions. So we said, okay, we're going to steal 1 bit, and the bit is going to be an indicator of whether the other 7 bits actually contain the term frequency, or if they actually have the position inlined. So now when can we inline the position instead of storing a term frequency? Well, we can do it if the term frequency is 1, because then we know we have exactly 1 posting for this document and this term. So now we can say, okay, if the term frequency is 1, we're going to set the bit to 0, and we know that the other 7 bits, as before, are actually the position of that single occurrence of the term in that tweet, right? There are some other conditions that have to be fulfilled in order for us to inline. They're kind of like implementation details. The text position has to be smaller than 127, because 7 bits can only store the value 127. So if we had a tweet, that had 140 characters and has like 140 tokens, and the token occurs at position 140, then we would not be able to inline that position because the number 140 cannot be stored in the 7 bits. But of course, that doesn't happen very often. Also, if we would use payloads, we cannot do it because with payloads, we know we have to store the payloads in the other stream. So that's why we would also not be able to inline the position here. And that's an implementation detail. We cannot actually inline it if a posting is right behind the skip point for kind of complicated reasons. Yeah. Okay. So the summary here is that we can now support with this format 32-bit positions, and we can support payloads. And we still keep the optimizations for tweets. We still keep the fact that doc IDs are stored in 32-bit integers. We keep our entire threading model. We keep optimizations for tweets where we can inline positions. In 99% of the cases, it actually is just inlined, and we don't currently in the tweet index have to use the additional data structure. Skip lists are actually now introduced. They improve performance of especially Boolean queries, and we use them as these synchronization points to find quickly where in the other data structure the corresponding data is. And for short that's what I said already. And the performance and space consumption actually now of this format is almost identical to the previous format. So we added all these new features, but the performance you can almost in our graphs you cannot see when we deployed this because the performance is so similar. And also the size of the indexes is almost the same. It's slightly bigger, of course, because now we have skip lists, and sometimes maybe we cannot inline a position, but then it's almost not noticeable. And that is pretty much it. And now I'm open to questions.
I have one question regarding your real-time search. I don't really understand why the basic Lucene index cannot provide such functionality to you. Why do you implement your own invert index?
Yeah, good question. The answer is what I was trying to hint at earlier, the way Lucene does near real-time. And Lucene is called the near real-time search feature, right? So the index writer, are you familiar with Lucene's API index writer? And that, yeah. So if you append a document to the index writer, it puts the terms and the postings into similar data structures as the ones that I talked about. But these data structures are not searchable. They are kind of internal buffers. So now they're appended, but they're not searchable. If you call open index reader on the writer and get a fresh index reader that can search these latest documents, what the index writer actually does, it needs to flush these in-memory buffers to disk or to a different in-memory RAM directory. So it flushes them. It converts the whole buffer into a different format. So if you call, in our case, we actually open an index reader with every single query. Like we get, as I said, 2 billion queries per day. Every single query is calls open index reader. Because for us, it's a cheap operation. I couldn't talk about the threading model, unfortunately, for time reasons. But that threading model allows us to open an index reader super efficiently, and that actually doesn't trigger a flush of this in-memory buffer to a different to a disk or to a different RAM directory. Right. If you would do the same thing in Lucene, if you would every single time open a new index reader, it would every single time, probably after every tweet or every 10th tweet or so, flush that stuff to disk or to the RAM directory, and then you would actually later pay for that because it has to merge all these segments together. Lucene would start segment merging. So what you actually, what the problem then is in Lucene is that the more often you call open index reader, the more your indexing performance goes down, because the index writer will be busy with segment merging. In our implementation, we completely decouple indexing and searching. So you can, as I said, you can call 2 billion times open index reader per day, and we never flush anything to disk, and we never have to do segment merging. So the indexing throughput, like if you look at a graph of Earlybird, and it's not accepting any traffic, it's just indexing, and then you start hitting it with queries, you don't see a slowdown at all in the indexing performance. So that's pretty much the reason why we are doing this. And that's why all these data structures have to be a little bit more, I don't want to say complicated, but they have to meet other requirements for threading reasons for the way our concurrency model works. Yep.
Yeah, I have two questions. One's just a detail. I'm curious if you have more, like dock frequencies bigger than 127, you just repeat the
good
posting?
question.
That was one. I assume you just repeat it like you did in the old system? No.
No. I took that slide out because I thought it would be too many details. But it's actually pretty easy. We just store the value 127 in that spot, in those 7 bits, and we store the actual number then in the secondary data structure.
Okay. Yeah. So, and then the other question is just about, have you compared the size of the indexes with the variable length encodings that Lucene has, and what are the trade-offs likely to be?
Yeah, we have about, I want to say, 30% more space compared to a Lucene segment. What we do is actually the segments that are complete. Remember, I had the incomplete ones on the top, and in the blue box I had the complete ones. We actually, when they are complete, we start compressing them in a very similar format to Lucene, and then we kind of reclaim the space. So we actually only pay that 30% overhead for the most recent segments. But that's actually not even a fair comparison at all. The fair comparison would be to compare this encoding to that in-memory buffer in Lucene that is currently not searchable. Because I haven't compared those two. Likely Lucene's is smaller because they can actually use VINs. They don't have to fulfill those threading requirements. But that would be a more fair comparison to compare those two.
Okay, thanks.
Yeah.
When you talk about contributing this to Lucene,
yeah.
Does it mean that a single index will be limited to 16.7 million documents, or segments above that number won't be merged anymore?
It would mean that we would have to flush the buffer after 16 million documents. You can still have bigger segments, but what I talked about earlier, like right now, Lucene, when you call open index reader, it flushes this data structure into segments, right? I think in this case, it would just mean we could delay that flush until we reach 16.7 million.
Okay, so it's only the in-memory representation.
Yes.
Okay.
Yeah. As soon as you flush this, as soon as you kind of compress this, you would actually convert it into like the standard Lucene format. Yeah. Which is in fact something we are working on, that even for those complete segments, when we optimize them, that we don't use a custom format anymore, but we're going to use a vanilla Lucene format. The only thing why that's a little tricky to do right now is that we have a custom implementation of doc values, because we need to be able to update them in memory. That's why currently it's a little tricky for us to just convert what we have to vanilla Lucene, but we are working on it. Yeah, in the back?
Just occurs to me this seems very similar to the kind of problems you would have to solve for log analysis. Have you thought about splitting Twitter and opening up a log searching business as well?
I have not personally thought about this. No, yeah, but I mean, I think this would be a good use case, a good implementation for a lot of use cases that require real-time access to your documents, and where you have, it's really good approach for use cases where all your numbers are high. Your numbers, your documents per second, the number of queries you have, and especially the latency that you have to meet between indexing and searching. So whenever you have a use case where all these numbers have to be very high, well, the latency very low, then this is a good approach. Anything else? All right.
Hi. What about facetting? You on Twitter you can search, but it's impossible to have some facets about the result. Is it because you have this early termination about on the search?
It's a good question. Actually, we have some sort of faceted, or we have technologies that are very similar to faceted search, but kind of hidden from the user. If you think of a use case where you want to return, well, it's basically faceted search, right? If you want to return in an index where the documents are tweets, you want to return results that are not tweets, that are, for example, photos. Photos could be considered a facet, right? You could build, of course, an index only made of photos, but if you talk about a real-time use case like Twitter, that's very hard because maybe you see the photo, now, and in the next 10 minutes, people are going to comment on it or tweet about it. So when are you going to index that photo, right? Because all the text is kind of metadata of the document, but you're going to see it later. So for that use case, the faceted approach is actually pretty cool because now we can index for every tweet that has this particular photo. We can identify, okay, that link is a photo, and we can assign an ID to it. And now we can actually facet on these IDs. So you could, for example, search for, when I say best photos in San Francisco, your query, would be San Francisco, and we find every tweet that matches San Francisco. Look up this ID look up what facets this tweet contains, and the facets are, for example, this photo, and then have an accumulator that counts which IDs occur most often in the results. But yes, you're right. Early termination can be a problem. But basically what the answer is that we just keep searching longer. I mean, we would probably still not search if you want to find the best pictures in San Francisco. We're not going to search all 300 billion tweets, right? So we search more, but we also early terminate at some point. But yeah, we don't have this classically exposed facet feature. It's more like where people can click filters together. It's more like used under the covers for these kind of use cases.
Could you tell a bit of how you deal with cache flushes, or do you even care about them?
With what?
Cache flushes, So like I'm asking a bit from the Solr perspective. So every time you commit, your cache flushes.
Flashing caches. We don't commit. It's all in memory, right?
So is it so that you always search backwards in the most recent segment and it's fast enough for you?
It's all in memory. There's no caching here. All segments are in memory. The ones in the real-time index, they are all in memory.
And it's still fast enough?
Well, I don't answer the question. I mean, caching is also memory, right?
Yeah, but cache can have different data structure.
Oh, yeah, you're
specifically
talking
for fast search,
Okay, I thought you maybe meant the file system cache. So you're meaning specific query caches, or?
Yeah, query search cache, basically.
Okay. Sorry. We do have some caching. We have different caching approaches. I think I may have talked about one last time here, which is we can cache partial results. So for example, let's say you have certain operators you always append to every query. For example, when you enter San Francisco, what you really search for maybe is like San Francisco and not from spam users and do not contain offensive images. I don't know. Could be something, right? That's not really the query, but that's an example. So let's say we append always these operators, no spam, no offensive content to the query. It wouldn't make sense to always really join these operators in. So then in that case, we have kind of what we call the query cache, where we can actually cache partial query results. So for example, no spam and no offensive content. The merge of these two operators, the result of that we can actually cache in memory. And next time someone enters a new query, we don't have to evaluate these two operators again. We can actually just join with the result set. The interesting part is how we do it with real-time search. Again, if I believe it was in the last presentation. If you look at this talk, that you can't see right now because the screen doesn't show the bottom of the slide, but there's a link down here which links to the previous slide from Barcelona, and actually that, I think, covers how this cache works. And then we have other caches in the system, like the Blender that I talked about. If you issue the exact same query and like 1 millisecond later, it's going to hit that cache in a lot of cases, not in all cases. So there's kind of different caches in the system.
But you have to flush it sometimes, right? Because you get new data, so you have to flush the old cache or rebuild it somehow.
Yeah, so
This is my question.
This cache that I was talking about, the way we update it in the real-time case, it's a little bit, it's hard to explain that without slides. Again, in this talk, I explained how it works. We have kind of a background thread that while you're pending posting this, you can also update the cache, but sometimes you also rebuild the whole thing. Yeah, so we have some approaches to do this efficiently.
Yeah. Okay.
Yeah.
Thanks.